Today we are going to talk about velocity. We have already discussed speed, which is the scalar version of how far, and it is measured in meters per second. And so we define speed as being the ratio of distance over time. So how many meters did we travel divided by the amount of time that it took us to travel that distance. And ideally we want our distance in meters and we want our time in seconds. When we talk about velocity, we are going to continue to evaluate how far an object traveled, but if we look at this definition, velocity is now going to be defined as a vector, whereas our speed was classified as a scalar quantity. So today's new vocabulary word is velocity, and we want this to be a vector value. So that means that when we look at our definition of velocity, this is defined as our displacement over time. So if we remember that vectors are variables where the direction is included, then it makes sense that we are using displacement in time versus distance in time. We are still measuring our velocity in meters per second. And so now when you read a question, you are going to have to pay close attention as to whether they are asking you for the speed, which is going to be the scalar version where we are taking the distance traveled divided by time, or if they are asking you for the velocity, where if we have both positive and negative motion taking place, you would then have to determine the displacement overall for whatever segment or motion you are being asked to evaluate, and then take that displacement and divide it by time. So understanding the vocabulary is really important. At this point, you are expected to know the difference between distance and displacement. So when we define velocity as being displacement over time, that should have a different meaning to you. When we say that velocity is a vector, you should immediately tell yourself that you are going to use the displacement how far, because that is the vector version. Okay, so things like that are expectations at this point based off of your knowledge of the vocabulary. If we look at our formula here, we have V is equal to delta D over T as our equation. So when we originally defined what our speed was, we said speed was going to be V equals D over T, where the speed was the v, the d was the distance, and the t was the time. If we look at today's equation, it's very similar. The only difference is that now we are telling you that your numerator should have a delta in front of the d. So let's just review. This delta means change. So this means change, and anytime we are going to calculate the change in a variable, we will be finding the difference by taking the final value of that variable minus the initial value of that variable. So for our in-class purposes, I am not going to be writing two formulas on the board for you. I am going to leave it V equals D over T like we've already received. You will have to be responsible for knowing that if it's asking you for the speed, that D represents the scalar distance. If it's asking you for the velocity, then that D technically represents delta D, because that would be the vector displacement. So I believe that you guys are capable of that. The expectation is that you will know the vocabulary well enough that you will know whether that numerator is technically a d distance or a delta d displacement. So just be warned that whenever you are looking to the list of formulas, this is how we're going to write it for both speed and velocity. All right, just a friendly reminder that we are going to be using the guess process whenever we work word problems, and we'll be working on some more word problems throughout this chapter. We're going to get a variety of equations in this chapter, and so we will be reviewing this process as we add more formulas to pick from. So just want to make sure that we are practicing the guess process on every single one of our math problems throughout the course. This is the graph that we looked at last week or in the last chapter, where we were evaluating how to read a distance time or a position time graph. And so we started off by just simply analyzing the y-axis shows me my values in meters. And so this could be where I look if the question is asking me where the object is located, aka the position. If it's asking me the distance traveled, if it's asking me the displacement, we're reading the y-axis. The x-axis is our time. And so therefore the slope on this particular graph is going to represent our speed. And so we talked about how we are always going to have positive values when answering questions about speed. So we're going to take a moment, we're going to review some of that information. Ideally, everybody is confident with the answers that we're going to go over right now. If not, please get the help that you need to get comfortable with it, because this was from the previous lesson. And so the idea is that by now you've mastered how to read these things. And so we're going to talk about a couple of things that are a little bit different, some more details that we're going to be able to pull off of this graph now that we are looking at velocity as a vector. Okay, so I have a list of questions or things for us to evaluate on the slide, so we're just going to go through these. It's asking us to describe the direction by saying right, left, forward, back, positive, negative. The directional references are going to vary depending on the questions that you are given. As long as we understand that right and left are going to be opposites, where one is assigned a positive value and one is assigned a negative value, that's the most important thing for right now. I'm going to keep most of my explanations over the next couple of lessons in the right-left directional reference. As we start evaluating vertical motion, we'll change that up a little bit, but right left is the most common form of question you will receive at this point in the semester, so I'm going to use those labels for most of our conversation today. So when we are looking at this very first segment, segment AB, we would say that this motion is to the right. If we were talking about the kind of slope that we have here, this would be a positive slope. So a positive direction would be right versus a negative direction, which would be left. Okay, this could also be called forward, and this could also be the positive direction, depending on how the question is worded. For segment BC, don't be tricked. If we ask you a question about direction, I need you to understand that my object is at rest here. There is no direction, okay? If my object is not moving, or if my object is at rest, then we do not have a direction. Sometimes students want to say right because right was the last direction. There is no direction for a moving object. And in the future, I want you to answer all questions so that we clearly state there is no motion for this particular segment. For segment CD, our object is now moving to the left. If we were in math class, we would evaluate this as a negative slope, so this would be motion in the negative direction. And then if we are looking at DE, this is also motion to the left. This would also be a negative slope. Okay, so these are things that hopefully you already feel comfortable with. The next thing that we're going to review is what is the distance traveled in each segment. So if we are traveling from point A to point B, then we traveled a distance of 5 meters. If we are traveling from point B to point C, well, we're actually not moving at all, so that is 0 meters. If we're going from C to D, I am moving from the 5 meter mark to the 0 meter mark, so I have traveled 5 meters. When we are talking about distance, this is scalar, so we're going to officially write that as a positive 5 because direction is not important for the vocabulary word distance. And then when I'm down here from D to E, this is also 5 meters because from 0 to the negative 5 meter mark is still just 5 meters away. It is in the negative direction, but for right now, we are evaluating distance. And so it's just a plain 5, okay? Now the next question is asking us about the displacement. So now we're going to clear this off. When we talk about displacement is going to ask us from the beginning to the ending, final to initial, okay? So if we make multiple stops along the way, we're ignoring those. We're looking, my very first point is A, which gives me a value of 0. My very last point in this particular segment is C, which gives me a position of 5. So from final to initial position, we are at position 5 minus 0. That gives me 5 meters. This is a positive 5 meters for my displacement. The next question is asking us about segment A to D. So for A to D, we are starting off at point A, we are ending at point D. So my position is 0 and 0, final minus initial, or we came back to the same spot. So my displacement for AD is 0 meters. When I look at the last question, it's asking me to go from point A to point E. So A is at 0, E is at a negative 5. When we follow the format, remember displacement is delta D. So we are going to say final position minus initial position. This leaves me with a negative 5, and because displacement is a vector, we are going to include that negative in our final answer. Remember, if this is a quiz or a test, we're going to technically make these 5.0, so we have a minimum of 2 sig figs. Now down here at the bottom, it's asking us about calculating our slope. Our slope is rise over run. So if we are looking at our slope value for segment AB, what we would do if we were in a math class is we would say y2 minus y1 over x2 minus x1. So for segment AB, my y2 is 5 minus my y1 is 0 over, I ended at 1 second of time. I started at 0. Excuse me. So this leaves me 5 over 1. It is a positive slope. I calculated a positive value. So my slope here is a positive 5 meters per second because my rise or my y value was measured in meters and my run was measured in seconds. If we go from segment C to segment E, we're following the same format, final minus initial. Y2 minus Y1 is going to give me a negative 5 minus 5 because we're going from C to E, divided by, and then for this segment, sometimes students work a little too fast and they just throw a 5 in there because E ended at 5 seconds. Please be careful, take your time, read carefully, look very closely at the graph, especially when you're working on a quiz or a test. Don't make these silly mistakes. Follow the format. The equation says that I need to do x2 minus x1 as my run, and so let's take time to actually write those in. I know it may feel like extra unnecessary work, but we really want to make sure that we are working carefully, especially for our quizzes and tests. So x2 is going to be 5 seconds, x1 is going to be 3 seconds. So instead of having a 5 in my denominator, like a lot of kids would do just from being careless, my denominator is actually a 2. And then in my numerator, this is another common mistake that I see kids make. They see a 5 minus a 5, and they just immediately make that a 0 in their head. This is negative 5 minus 5. I'm just getting a larger negative. This is going to give me a negative 10. So I calculate a negative 5 for my slope. This tells me that my slope has a value of 5 meters per second while moving in the negative direction. If we look at our graph and we think about ourselves being in math class, we would call this a negative slope, and so it makes sense that our slope value would be negative. So now whenever we are looking at our velocity values, if they are asking me, like question number 6, what is the velocity for segment DE? They're really just asking me to calculate the slope. So we need to understand that the slope on this graph is the velocity. If we are calculating the slope using y2 minus y1 over x2 minus x1, it will officially calculate positive and negative numbers. And so now we're going to keep those negatives, because those negatives are going to be part of the answer because velocity is vector where direction is important. So if they're asking us to calculate the slope for segment DE, I would do rise over run, or I would do, in this case, I would have a negative 5 minus 0 over, what would that be, 5 minus 4, and so that's going to give me a negative 5 over 1. So my slope here is just going to be a negative 5 meters per second. All right. So now we are looking at the same graph, and so we can take some time to do some extra practice, but I think we have the idea. The biggest thing that I want to make sure that you guys take away from what we're adding to the lesson today is that when we calculate our slope, we want to make sure that we are very specific in our format. Final minus initial when we're plugging those values in. And if it spits out a negative number, then we need to keep that negative because that's part of the answer. So let's look down at the last two questions on this slide. It's asking us to calculate the average speed for this graph, and then it's asking us to calculate the average velocity. Let's just review how we do that, because my answers for these two are going to be different. Even though they're both asking for me to evaluate the whole graph, the meaning of the word speed and the meaning of the word velocity affect how I'm going to execute my calculations. So when we are dealing with speed, remember, is my distance divided by my time. So we are going to take the total distance for this whole graph. So in this particular question, we go 5 meters for the first segment, 0 meters here, so I could say plus 0 if I wanted, sure. And then we travel 5 meters for segment CD and an additional 5 meters for segment DE. So when I am figuring out what number belongs in my numerator, I am going to have to account for all of the motion that was traveled. So my numerator here is a 15. You add up the sum of the absolute value of all of the motion. That's why all of these values I've written down are listed as positive numbers, because distance is scalar where the direction is not important. So we won't include negatives here. My time for this graph, we started at 0, we ended at 5, so it's just 5 seconds of time. So my speed here is going to be 3, or 3.0 if we're taking a test, meters per second. When it's asking me for my velocity, velocity is going to be the vector version, where this is my displacement over time. So now I am not going to be concerned with all of the motion that took place. Now I am simply going to look at my ending point and my beginning point, and those are the only values that matter. So delta always means final minus initial, and then once again we're using the full 5 seconds of time, so I get negative 5 over 5, which gives me a value of negative 1.0 if we're taking a quiz or a test. All right, we are now going to take a moment and we're going to look at these two graphs. Normally I pause for a while here and I ask my students, look at these two graphs and tell me, do these two graphs show the same motion? Well, the correct answer to that question is yes, they do. Now, a lot of times students look at these graphs and they're just not really sure how to evaluate the second graph, or they're not careful enough to read the labels on the second graph, and they don't realize that it's got a different set of labels. So remember, rule number 1, whenever you are given a graph, is to always read your labels. The graph here on the left has position listed as the y-axis. So this is the same type of graph that we've been looking at. The graph on the right has changed the y-axis. Now the y-axis gives me my velocity, and changing the title of the y-axis changes how we evaluate the graph. So we're going to look at this graph one segment at a time, and I'm going to show you how it does indeed show the same motion. We'll start off with this very first segment, segment AB. So since we know the graph on the right is showing us our velocity on the y-axis, I'm really just going to talk about velocity on the position time graph. So if we're looking at the position time graph, our velocity here is going to be the slope. So the slope is the velocity on this position time graph. So basically, I'm calculating my slope here. My slope is going to be rise over run, 5/1, which gives me a slope value of 5 meters per second. If I look at my graph on the right, because my y-axis is titled velocity, this says for segment AB, we are steady at a velocity of 5 meters per second. And that is what the other graph showed. So these two are showing the same velocity for that first segment. For segment BC, now we are looking at an object with a steady position. If we're looking at our position time graph, my position does not change. My object stays at rest. My object does not move. My slope value is 0. So this object has a slope of 0 meters per second for segment BC. If we come over to my velocity time graph, here is my value of 0 meters per second because the y-axis is showing me velocity. So when I look at segment BC, sure enough, we have a steady value of 0 for this particular segment. When we look at the position time graph, and we are over here for segment C to E, once again, the slope gives me my velocity. So if we calculate slope, it is rise over run. So we would put in a -5 minus 5 over 5 minus 3, which gives me a -10/2. So this whole segment has a -5 meters per second value. When we look at the graph on the right-hand side, C to E shows a steady value, and if we look at the y-axis, that is a value of -5 meters per second for the entire duration. So I want you to be careful whenever you are given a graph. Always look carefully at your graphs to see what your labels are. The labels will make a difference as to how we interpret that graph. So at this time, I'm just going to give you a sneak peek at one of the graphs that we're going to be looking at for the next lesson. So when we talk about a velocity time graph, we are going to be now looking for the y-axis to give us information about the velocity. And then we're going to have to figure out what does the slope on this graph represent, because it's no longer velocity. Velocity has already been written on the y-axis, so the slope must be something different. And so we'll talk about that in the next lesson. One thing that's different in this class versus math, I know that I say this a lot, but we use math in physics. This is not a math class. So if we were in math class and we were given a value of -5, you would typically say that that represents a value that's less than 0. And that is true when we are in math. Negative numbers are less than 0. However, in physics, this represents real life motion. So let's say that this graph is showing you how my object is moving in real life. So let's make the object the car. If I am in my car and I'm in the student parking lot, this could very well be a graph that shows how I am moving in the parking lot. So let me ask you a question. The speedometer on your car tells you the speed, how fast you are going. How could you physically accomplish a speed of less than 0? Because if we're looking at this graph, and this graph says that I go all the way down to a velocity of -5, we see point G is at -5, how would I physically accomplish that in my car? How can I go less than 0 miles per hour? Well, the answer to that question is I can't. I can't physically go less than not moving at all. I can't go any slower than being still, right? So Here's a situation where we have to understand the concepts that these graphs are representing. We have to understand the meaning of the vocabulary so that we can then evaluate this information correctly. So what I want you to go ahead and start processing is that if we are reading a velocity time graph, as we move away from the x-axis, as we move farther away from 0, along this velocity axis, we are increasing in speed. My speed is getting larger as I move in the positive direction. I'm going to say that again. As we move away from the x-axis, or as our y value gets larger, we are increasing in speed. I am moving faster in my car as the numbers move away from 0, except on this part of the graph, I am simply moving in the negative direction.